welcome to today's class. I'm glad to have you here. In our previous lesson, we discussed the concept of refraction of light through plane surfaces. And we used, for example, the rectangular glass block. And we said if light is incident on a prism, or if light is incident on a material, two things will happen. One, part of that light will pass through, and the remaining will be thrown back, and that is, will be reflected. And we have a plane like this. We have a normal line because this is our angle of, this is our incident ray. Make an angle here, angle of incidence. We have that if this ray, on getting to this point, this interface, it will bend away from the normal. Once it bends away from the normal, on getting to this place, it will come out again. Now, our interest is on this one, which is the refracted ray. This one is the emergent ray. Remember, an angle is formed here. So this is what we discussed the last time. Please, for details of this, see the link in the description below. Now, we want us to look at total internal reflection of light on a material. But before that, if you have not subscribed to this channel, please hit the subscribe button, hit the like button, and then share this video with your friends. Now, let us go. Now, for total internal reflection of light, of course, this particular topic comes out every year. I want us to look at the behavior of light when it passes through air and glass water interface. We'll have this, and then this is figure A. I want us to have another one here, figure B. And I also want us to have another one here, figure C. Okay. Now, if this is a prism, now we have here as glass. We have this point as glass, and we have here as air. Now, if we incident lights at this angle, this is angle of incidence here, this light will refract away from the normal. Now, if it refracts away from the normal, here we can have strong refraction. There is strong refraction here. Now, remember we said two things will happen. Part of this incident light will pass through. This is the one that is passing through. Now, the other part will be thrown back. It will be reflected. Now, assuming we have here as, let's say, YR, and then here is S. YR, and then YS. Let's say, here we can have here as X. Now, in the first place, here is our angle of refraction. If light is incident on the surface, now the part of this ray will be refracted. That means this is the ray. It will bend away from the normal. Now we have strong refraction here, and we'll have a weak reflection. This reflected ray is weak because majority of the ray is refracted. Now we have this. Now for B, we can have it B here, figure B, which is something with A. Now, if you increase angle of incidence, or you continue to increase your angle of incidence, let's say we have this. At this point, this is our angle of incidence. If we now increase our angle of incidence, the angle of refraction, let's say we can have it somewhere here. Angle of refraction. That means the whole of here is refracted ray. Now, here will give us the reflected ray reflected. So we have this one is still strong refraction. And then this one will give us weak reflection. Weak reflection. So as you continue to increase your angle of incidence, angle of refraction increases. The refracted ray is further bent away from the normal because this is a normal line. This side is a normal, this is a normal line. It continues to bend further away from the normal line. Now, as we have figure C here, still the same thing. If we have such, now let's say angle of, this is our angle of, this is our incident ray. Continuous increase of angle of incidence, this is our incident ray. Now all the rays, this one there will be no refracted ray now because the refracted ray will now be along this line. So if we have this as our Y, R here, and this is our X, this is our S here. Now in this case, we now have Y here, R here. Now this X will now lie on this. That means at this point now, the angle of refraction now is 90 degrees. That is, at this point now, we say R is 90 degrees at this point. Now, when R is 90 degrees, that means we have strong reflection here. At this point, it's becoming, though the reflected ray will still be weak reflection. Weak reflection will occur. Now, at this point, where the at that particular angle of incidence, where the angle of refraction is 90 degrees, will now give us what we call critical angle. So at this point, we can now define critical angle as that particular angle of incidence where the angle of refraction is 90 degrees. That is the critical angle. Okay, now if we continue to increase our angle of incidence, if you look at this, follow the direction. We have a smaller angle here. We increase it here, and this one increased. As we increase further, angle of refraction will now lie on the air. Remember, this is the glass. This is glass here. Y here is air. Here is also glass. Y here is air. Now, as we have the next one here, where we have here, this is glass. Here is air. Now, if we further increase our angle of incidence, this is our angle of incidence. Now, all the rays, this one, now instead of lying on this the glass air interface, all of them will now pass through. All of them will now go back, and then all of them will now pass through. In that case, there is no refraction here. There is no refraction at all. There is no refraction at all. No refraction at all. Whereas here, there is refraction here. But the refracted ray is now lying along the glass air boundary. So we now have, this is a refracted ray here. Refracted ray in this point. Now, in this case now, no refraction. All the rays has been so we have, at this point now we have a strong, when there is no refraction at all, this point will have a strong reflection. At this point now, we have strong reflection because the reflection here is strong. All the rays incident on this glass prism has been totally internally reflected. So now at this point, we can now define total internal reflection of light as a phenomenon that occurs when light travels from a denser medium to a less dense medium as the critical angle is exceeded. And we can also say that yes, total internal reflection of light is a phenomenon that occurs when the critical angle is exceeded for light traveling from a denser medium to a less dense medium. Of course, in this case, now, when light travels from a denser medium to a less dense medium, that light is totally internally reflected. Now, let us look at the conditions for total internal reflection of light to occur. Please, every year, questions continue to come out, especially during the WAEC question. They usually ask questions from total internal reflection of light. Now, let us look at conditions necessary for total internal reflection of light to occur. One of those conditions is that, one, the critical angle must be exceeded. Remember, we said that at this point, this is a critical angle where R, that particular angle of incidence, where R is 90 degrees. So at that point, the immediately we exceed critical angle, all the rays will reflect back internally. So one of the conditions is that, one, the critical angle must be exceeded. Two, light must be traveling from a denser medium to a less dense medium. So these are the two conditions for critical angle, for total internal reflection of light to occur. We want to look at applications of total internal reflection of light. By application, we mean uses of total internal reflection of light. Of course, total internal reflection of light in the present day has about 5 or 6 uses or more applications. And of course, one of the applications is that, one, it is used in prison periscopes. It is used in prison periscope. Two, it is used in prison binoculars, or they are used in binoculars today. So the principle of formation of prison binoculars is based on this total internal reflection of light. Total internal reflection of light can also be applied in optic fibers or in fiber optics. Yes, it is used in fiber optics. It can also be applied in fish eye view. And of course, when the fish, because the fish is in water, the refraction takes place there. Of course, because of refraction, it can be, that is why we now have that, yes, it is applied in a fish eye view. It is also applied in the transmission of radio signals. It can also be applied in the projection lanterns and cameras. Then, finally, we can say that total internal reflection of light can be applied in mirages. Now, by next lesson, we are going to look at how we can use this total internal reflection of light in fiber optics. So, if you have followed me up to this point, please join me in my next lesson where I'll be treating the fiber optics and the lasers. Do not miss that lesson because it's going to be hot. Now, if you have not subscribed to this channel, please do me this favor. Hit the like button. Tell me something in the comment section because that is what motivates me to continue to create more videos for you. See you then. Thank you.